Hi, good evening. Am I audible? We'll wait for a couple of minutes and we'll get started. In the meanwhile, let me introduce myself. I am Durga Prasad. So I'm a third year PhD scholar from IIT Madras. So I'll be organizing the live sessions for this particular course for over the next 12 weeks or 13 weeks, depending on the requirement. And the main aim of these sessions is to help you clear your doubts, at the same time also discuss some of the problems so that you can solve your assignments. Since the assignments are graded, I wouldn't be discussing them directly, but if you have any doubts regarding the questions or the way they are phrased, we can discuss them. And once the solutions are out, if you have any doubts in them, then also we can discuss them. So just wanted to know how many of you have already gone through the lecture videos before? Yeah, you can either unmute yourself or you can type it in the chat box. Up to you. Okay. So you have any queries? Okay, so I guess the remaining have not gone through. Okay, then maybe we'll have a quick recap first and then we'll discuss the problems. I've just listed on only the main points from the lecture videos. So like these are kind of a summary. So you might have to actually go through the entire lectures again to better understand the context of them. But the main points are as follows. Obviously, the optimization, the main objective of optimization is to find some best alternative from set of feasible. Will you have these sessions every week? Yes. Ideally, it is expected that you have gone through that particular week's lectures and you attend the session so that if you have any doubts, we can discuss online. Of course, even if you go through later, you can always post your queries on the discussion forum. We can discuss those questions as well. But if you want to discuss something in the live session, then you can have it. So you can come prepared for the session as well. Yeah. And any of the material that I will be using here will be shared with you on a Google Drive that will be provided to you at the in the same course website that you are attending. So I think NPTEL is actually responding to that. So I work on applying engineering for building energy systems, mostly related to fault detection, diagnosis, and then some of the CFD stuff as well. You happen to be from IIT Madras. Okay. Yeah. I think we are 5 minutes past, so we'll just get started with the session. I'll quickly go through the recap of the lecture videos, some of the main points, some of the theorems, and then we'll solve some of the problems. The first week is more of an introductory thing, so we don't have any detailed problems as such. So I would prefer if you would actually involve in the discussion, maybe answer some of the questions, so that we can wrap it up much faster this week. Maybe from next week we would have to be requiring the entire 2 hour session. Okay. So how many of you have actually gone through the isoperimetric problem? So would you like to discuss it? Okay, 3 people. Good. So the main idea in isoperimetric problem, so the main broadly there are 3 points. You start from some feasible point, or you start with some initial closed loop, and then you find ways to improve it, and you keep doing this until no further changes are observed. That is the whole process that we followed in the isoperimetric problem. You start with some arbitrary shape, and then you identify that if you have anywhere you have concavity, then you can always try to maximize the area by changing it to concave to convex, and then you keep doing it by applying symmetry principle and other stuff. But whatever be the problem, the main idea is we start with some feasible point, and then we find ways to improve upon it, and then finally we will keep doing this till no further changes are observed. And this particular process will give you a solution if a solution exists in the first place. So the main problem that the professor was trying to address there is how do we know that a solution exists without actually solving it? That's where the entire lecture series starts, and that's the first week. The entire first week lectures is about how do we identify that a solution exists in the first place. Only if the solution exists, then we can apply this particular strategy. And this is a framework that we'll be using throughout the course. You will find we'll just come up with different methods to see how we can improve upon our initial guess. So we start with some initial guess, some feasible point, and then we try to move from one point to the other point by using different ways. You have third attempt related to the hinge. Okay, just a second. I'll just share my screen. Is my screen visible? Sorry, I can't see the Google Meet screen because I'm sharing them. So can you please unmute yourself? Let me know if my screen is visible or not. It's visible. Thank you. So the third point is essentially related to how. So once you have decided, like once you know that you need a symmetry inside the problem, so that if it is asymmetric, you know that you can always change the other one to follow the symmetry so that you'll get the maximum area. The next part is here we take a particular length of this. So you consider any 3 points on this particular arc. You know that this has to be an arc. We do not know as of now like what kind of arc it is, but it is some arc. It is some curvature like this. So we pick 3 points, and then what you do is you fix one of them. This is your hinge. So imagine you can move this line and this line independently around this particular hinge point. At the same time, this point and this point are also fixed. So you can think of this as so this is a rope, and then these are some two sticks that you have, and then you are actually tying that rope to the stick at these points and these points, and you are fixing this as a hinge, and then you are moving this, so it appears something like this. So you can tilt this, so you can change this angle continuously. So that rope length will still remain the same, but the shape will actually, like the length of the rope will remain the same, but that the curvature will actually change. Is this up? Is this part clear? You can always stretch this rope to the maximum area. Like since the length of the stick is constant, this stick length is not changing, and the segment of the rope that is attached to these strings at these 2 points is also fixed. This area will always remain this area will always be a fixed area. Similarly, the same logic applies for the other half as well. This portion also you'll have the same area. So the shaded area will always be a constant. So the total area will be maximum. The total area covered by this particular curvature or particular arc will be maximum if the area of the triangle is maximized. Like we always know that area of triangle is half into base times height. So this particular dotted line here will be your perpendicular distance height. Or you can also think of it, use your sine rule, half AB sine alpha. So this length is A, this length is B, and angle between them is alpha. So the area will be half AB sine alpha. And if you want to maximize this, the only way is to maximize, like put alpha equal to 90. That is when sine alpha will be 1, and that will give you the maximum area of the triangle. Since this is a fixed one, if the area of triangle is maximized, then the area of this particular arc will also be maximized. And when will that happen? When this is 90. So we already know that in a semicircle, if you consider any of these chords, then they intersect at 90 degrees. From that principle, we know that it is a semicircle and it has to have symmetry, so the entire curve will be a circle. Is that clear? Or are there any queries? Uh, since I can't see the chart menu when I'm sharing the screen, it would be better if you can unmute yourself and let me know if you have any doubts. Is this clear? Yeah, sorry. Uh, yeah, can you confirm me? Is this the query or you have something else to discuss? Yeah. Yeah. So what is the query? Supreme minimum is supposed to be part of the set being considered. Okay, we will get to that part. So this part is clear. So we'll just go in the same sequence so that we don't miss up on anything. Before the supermoon and infimum, to those of you who haven't gone through the lecture videos, I hope you already know what a sequence is. So you just take numbers in particular values. So, and then what you mean by convergence of a sequence. We say that particular sequence converges if you keep on going taking samples from that sequence. After a certain point, it doesn't change its value within the tolerance specified. So the most important point here is you always need to find that particular k beyond which these changes are negligible. Then this particular value extra is called your limit of that particular sequence. And if a particular limit exists, then it will be unique. These are some points that you might have to recall. You might have gone through all of these in your elementary mathematics or in your undergrad maths. So just kind of a recall. So if a particular sequence converges, then every subsequence of that sequence will also converge. What is a subsequence? Is basically you take the same sequence and you randomly take samples from this sequence, but then you ensure that you do not go in the backwards direction. You always take the elements only in the one way. Then if the original sequence converges, then all the subsequents will also converge, and all of them will converge to the same value. So what, okay, is the converse of the statement true? Let's say I have two subsequences, both of them are converging. Now I make a new sequence out of these two subsequences. Will that converge? Not necessarily. So it's not always true that it might converge. But if both the subsequences are converging to the same value, yeah, if both the subsequences are converging to the same value, then the original sequence will also converge to the same value. Otherwise, it may not be true. So why are we discussing all these things? It's essentially because in optimization, like as I said before, you start from some point and you keep on changing from your one point to another point. So this can be treated as a sequence. And once these points do not keep changing, that is what the last condition is. So you keep monitoring the objective function till no further changes are observed. We will come to this a little later. But now we are saying that the function, we do not worry about the function as of now. But if these points do not change at all, then it means that particular sequence has converged. And that is why we are discussing about when this can converge and when this cannot happen. So that's when the next theorem comes in the Bolzano-Weierstrass theorem. It says that when you have a bounded sequence, you can be pretty sure that at least one subsequence will converge. That is, after a finite number of evaluations, you are pretty sure that it will converge at least in one way. It may not be the right way, but it can be any different way. And the next point is where you have the lower and upper bounds. So as he was mentioned, I think someone asked a question before. We'll come to Supermoment infimum. So when your set is bounded, so all the values inside the set are within certain limits. You can have an infinite number of lower and upper bounds. Out of all these bounds, the one that is the largest of all the lower bounds is called the greatest lower bound, and the smallest of all the upper bounds is called the least upper bound. So this is supremum and infimum. So the question now is, can you make a set in which the lower supremum is not within the part of the set itself? I think that's the question. Supremum and infimum supposed to be part of the set being considered. So you are saying if you have an open set, then your supremum and infimum are not part of the set, right? Is that your question? Yeah, if that is your question, I think that's your question. So I think then it's no. This least lower bound and least upper bound and greatest lower bound need not be part of your set that you have considered originally. So okay, we'll come to open set and then we'll discuss that further. And then comes the completeness axiom. The way we have defined the least upper bound is essentially the upper bound. In case of a least upper bound, you have taken the minimum of the set of all numbers of all possible upper bounds as your least lower bound. So which means for a least upper bound to exist, you need to have a greatest lower bound, and vice versa. That cannot happen simultaneously without inherently believing that something like that exists, and that's where we have this completeness axiom. Then comes the concept of open set. Open set is one where we say a particular set as open when you consider any point inside that set, and then you consider a sphere around that particular point, and all the points within that sphere belong to that particular set, then you call that particular set as open set. So now here, if you have an open set, then what do you think the lower or upper bound will be for the open set? Do they exist or do they not exist? What happens there? Or maybe even before that, I should ask the question, can you consider a bounded set of, okay, a set of real numbers as an open set? Remove this part for now. A set of real numbers, the set of all real numbers, is it open or closed, or what is it? Yeah, I think the question is pretty, when set of all real numbers would be open. Yes. So set of all real numbers would be open. So what would happen for the lower bound and upper bound of that particular set? I think it's pretty obvious. That's what no one is answering. So if you have an open set, then you do not have any bounds. Is it why no one is answering, or you have any other answer? There is no GLBU LBB. Okay, there is no supremum minimum. That is one. Okay, you are asking. Okay, anyone who has any other opinion, like exists, doesn't exist, defined, not defined? Take an example, then it may be pretty easy to understand. So like take an open set. So let's say I have an open set, say 1 to 2, a set of real numbers, 1 and 2 are not included. So it is an open set. Does it have a lower bound or upper bound? It has lower bound and upper bound. So what about supremum and infimum? Do they exist? They should exist, but beyond the particular set. So they exist in the sense of a limit, but the value, that particular value, will not be part of that particular set. Okay. So you are saying 1 minus epsilon, where epsilon is something that is tending to 0, will be the greatest lower bound or something like that. Then how would you define it? Infimum of 0 to 1 is 0. No, the set of 0 to 1, you wouldn't be able to define it that way, right? So if you have the set from 0 to 1 without excluding the particular 0, and you take all the values to the left of 0, you can always find, like, whatever number you choose, you can always choose a number that is greater than that particular one. Like if you have an open set, uh, any ball you take at any point you take, you will always find another ball with some finite radius, and which means you can always find another point that is to the left or right of it. So you keep on going, but you'll never end up any of these greatest upper bound or lower bound. Like you'll have lower and upper bounds, but you cannot be sure that there is a unique lower bound and upper bound. Like they do not exist in that. And that's where this completeness axiom comes, that it specifies that it needs to be a bounded set of real numbers. Only when you have a bounded set of real numbers is when this GLP and LUB are defined. If it is not bounded, then this is not defined. And if they do not, I mean, this is how we say the existence proof. Like this is kind of an axiom. I think that answers your question. Yeah, sure. Okay. Then comes the three definitions. The set of open set is defined, and then a closed set is one where its complement is open, then we call that particular set as closed set. A compact set is one which is closed and bounded. And of course, you can have sets that are neither closed nor open, like the one he just mentioned. The set where you have 0 less than x less than or equal to 1. It is neither closed nor open. And then there are different operations that you can do on these sets. The union of any number of open sets is open. These are certain things that you can also review in your math books. And then comes the definition of continuity. So a function is said to be continuous at a particular point. So whenever you can always consider, you fix a particular epsilon within that particular tolerance, you can always find another y such that mod f of x, y minus f of x is less than epsilon within that ball of radius delta. As long as you can do this, so what this means is at any point, you consider a ball around it within that particular tolerance that you have specified, there will always be a sphere surrounding it. As long as this exists, then that particular function is continuous at that particular point. And if this happens throughout the domain, then you call that function continuous. Why do we need it? Is because if you have a convergent sequence, then the limit of the function on this convergent sequence will be the function of the limit value. So this is what we were referring to before. So all we need in our formulation, like in our previous strategy, is so we will monitor the objective function till no further changes are observed. And this will happen if I'm iterating in such a way that my sequence converges. If my sequence converges, then I have my function to be continuous. Then I can see that the value will converge, the objective function will also converge. So that's where the Weierstrass theorem comes. Here we have the three different conditions. The function needs to be continuous, the domain needs to be closed and bounded. When all these three conditions are satisfied, then you can say that the f attains its minimum on that particular set, and there will also exist a solution extra. And we call that as your infimum of x or minimum of f of x in this particular case. That's the notation that we'll be using from in the lectures. Yeah, I know that this is a very kind of very fast kind of a recap kind of thing. So like I expected like most of you would have gone through the lectures. So these are just only the key points that I have taken from the lecture videos. So it would be better if you actually go through the lecture videos and then see, then it would be kind of refreshing before the session. Yeah, these are some very small questions. Yeah, thank you. Now we'll have like around 10 problems I have. We can discuss them. So these are pretty simple for the first week. So the first question is straightforward. So you can reply in the chat box with your answer. And then we can discuss if you have any, like see it from different perspectives. If, for some questions, if you have any views on this. So this is the first one is a straightforward question. So how do you find the limit as n tends to infinity for minus 1 to the n by n? Will it converge? Does it exist? Do not exist? What happens to this? Yeah, since these questions are kind of one-word answers, I would expect you to kind of give response so that I can understand if there are any problems either in the way I prepare the slides or maybe the type of questions I need to ask. So from next week I can change them. Limit is 0. Okay, anyone who says that it diverges or oscillates, converges, okay. Okay. I've just plotted it to see that it actually converges, but you don't have to do anything because minus 1 to the power n by this n will actually rapidly converge to 1 by n will rapidly converge to 0, so it doesn't matter about the number. So this is pretty straightforward. But can we say about this anything from the previous one? Like, can I create any subsequence from this that is not convergent or something like that? Like, this is my sequence. Can I convert any subsequence that is not convergent from this sequence? We have discussed this just before. Like, all the subsequence, any subsequence that I can construct from this sequence will eventually converge to the same line. So I will not be able to construct any subsequence from this. So that is straightforward question. Let's take another one. Yeah, this is also straightforward. So can I say every bounded sequence is convergent? So what do you mean by bounded sequence? Is all the elements are within certain limits. So Okay, one of you said true. Okay, what about others? False, 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 false. Yeah, most of you said false. So, okay, let's say who answered first. True. So, okay, can you give any example for the others? Like whoever is saying false, can you give an example why it is not true? Or the one who is saying true, can you prove it as true? So how did you go about the solutions? How do you know that it is not converging? Minus one, one, minus one, one. Okay. Yeah, you can also give a very simple example as sin x or something. So sin x is a bounded function, right? Like if your series goes as sin n or something. This is definitely bounded because sin n will always be between minus 1 and 1. But then it's not convergent. So why is sin n not convergent? Like which part of the convergent definition says that it is not convergent? Yeah, I know I'm kind of going a little more into math than discussing anything else, but that's pretty much the first week. So if you see the definition, this is the definition for convergence. So which part of this definition is not being true for the case of, for the example that he has given, minus 1, 1, minus 1, 1, or you can take sin x or whatever it is. So this is the definition for convergence. Not for all values epsilon, it's not for every epsilon. Not for all values of epsilon in the sense. So if I, okay, what is x star you are choosing? Okay, you have chosen x star to be say 0 or something, and from then you keep on seeing the values, and then I cannot choose for, yeah, for 0 or minus 1 1. You can chase, you can take any particular point, 0, 0.75, any point within the domain of that, and then you can always observe that for it won't be true for all epsilon for all n naught. You cannot find an n naught basically for which it will satisfy for all epsilon. Yeah. So one of you have actually answered true. Is it clear for you? I think it's clear, right? Yeah, this is also we have just discussed now. So let's consider the sequence xn is 1 by 2 to the power n. So if you construct a subsequence out of it, then the subsequence is convergent. So we have discussed this just now. So if you consider a sequence that is a convergent sequence, then all of the subsequences will be convergent. The question here is this xn, is this particular sequence convergent? I don't think there are any doubts in this, right? Yeah. So the next question. So I have a collection of open sets. Intersection of infinitely many open sets is open. Is a statement true or false? I would like to have a little more discussion. So maybe you can come up with some example, whichever answer you prefer. So if you say true, come up with an example that this is satisfied. If you say false, come up with an example that is false. And then we will see which of the examples is stronger than the other. How do you go about proving that statement that you have? Q3. Can I show Q3 for like 5 seconds? As in, yeah, okay. Okay, I think it's there. No, for the question 4, so I have a collection of open sets and I want to do intersection of all these open sets. What would happen? What can I say about the openness of the intersection? Will it be open, closed, compact? I do neither of the above. What would it be? Maybe I should put it slightly differently. So you have this is for infinitely many. Let's just say you have finitely many. Let's say you have two open sets, and I want to do intersection of these two open sets. Will I create any new boundaries by doing the intersection? An open set doesn't have any boundaries. The moment you have a boundary, you do not have points beyond that, so you will not be able to put a ball that have all the points within the ball being within the part of subset of it. That is not going to happen when you have boundary. So let's consider that particular case. So you have a domain here and a domain somewhere else, which doesn't have any boundary, like any boundaries, two open sets. And then I'm kind of doing an intersection of these two open sets. Will I create any new boundaries by doing the intersection? Yes, one of you told yes. What about others? Yeah. So you have a set of you have a collection of open sets. So when I'm doing the intersection of these open sets, will I be creating any new boundaries? Yeah, I just mean boundary, not closed, open, or something. Yeah, but that does not ensure that A will be open or closed. Yes. Yeah, like since no one was answering the original question, I kind of asked a sub portion of that question. So I have some open sets that do not have any boundaries. And if I do an intersection of such sets, will I create a new boundary? I just kind of asked a different question since no one was answering the original question. Okay, so it seems like you have answered yes. Okay, so if I have, let's create two open sets, 1 comma 2, and I want to do intersection with say 1.5 comma 2.5. So what would be the intersection of these two sets? Will it be, yeah, so 1.5 comma 2 is it an open or a closed one? If you are choosing the first one, this is an open one, right? Which means the bounds are not included. When you're doing intersection of any of these open sets, you are not going to create any new boundaries. So it will always, it won't be, it will never have a boundary, which means it will not have points beyond which you can go. Yeah, so you can always consider a ball such that all the, like there will always be some finite non-zero radius of ball that you can consider, and all the points within that ball will again belong to the same set. As long as you are not creating new boundaries, it can't become a closed set, right? Are you on the same page with me? As long as you do not create new boundaries, then it is not going to become a closed set. No, we are not there yet. So all we can say now is it is not going to be a closed set. We can always have sets that are neither closed nor open. So all we can say from this particular question I have asked you is that it is not a closed set. But there can be sets which are neither open nor closed. Say you have something like this. This is neither closed nor open. Or you can have singleton set. So if I have a singleton set, is it open or closed or what is it? Closed. Okay. Anyone else? Yeah, closed. Yeah, understood. What about this set? You can't make a sphere, so it is not open. If you can't make a sphere, it is not open. How do I define a closed set? If you complement it, let's say I just put this as complement. Of course, I shouldn't put like that, but let's say something like this. So the set that the all real numbers without zero, can I call that as open set? So this is basically a r minus zero. Yes, okay. Anyone who says no? The set of all real numbers minus zero. Can I call that particular set as open set? One of you have actually answered as yes. So what about the others? Is the question clear? Okay. I think now is no, okay, only one of you answered. So I think the question is not clear. Is that why no one is answering? So you have the set of all real numbers. Okay. So you also agree with him that it is an open set. Okay. Let's say I have considered a ball of some radius, or say I have at point 1, I'm considering a ball of radius 0.2. This will enclose 0 in it, right? This ball will enclose the point 0 in it. Which is not in the original set that I have considered, right? So if you look at the definition of open set, we say a particular set is open for all x belongs to S. There exists an r greater than 0 such that whatever ball you consider, all the elements in that ball should be part of that set. But here, this particular point, like if I consider this particular scenario, that is not being part of that set, right? How can I call it open set if it is not part of it? Yeah. Is this clear to everyone? Infinitely many open sets may not necessarily be open. Example in lecture, can't think of any other example. Yeah. Okay. So the one that we are discussing right now, r minus 0, yeah, that will eventually come there. So if you have a set like this, then it may not be sure that it will eventually go there. So the point is simple. When you have a particular set, you can think of this as a sheet or something in some high dimensional space. If you have some holes in that, then it cannot be considered open set. First thing, it should not have, like, whichever direction you go, you will keep on going and you will never found any bounds. You should not found any bounds. The moment you found any bounds, then it is not going to be an open set. If you poke a hole inside that surface, then it means that there are certain regions you cannot go and access, which means those are the regions that there are some boundaries there, and it fails to become an open set. I think this example is clear. Yeah, even as you pointed out, yeah, the recordings will be shared on YouTube and the link will be provided to you in the course website, along with the material that I'm typing out now. The entire thing will be shared with you. Yeah, the other example is as mentioned in the lecture, the minus 1 by n to 1 by n. That is also an example where once you do the intersection of all of them, it will be a singleton set 0, which is not neither open nor closed. So the main takeaway here is just because it is not a closed set doesn't mean it will become an open set. You can have sets that are neither closed nor open. That's just the takeaway from that. Yeah, now that you are sure, now you can answer this. So I have set of rational numbers q. Can I consider them as open? Yes or no? Can I consider the set of rational numbers as open? Yeah, is no, because at any rational number, finite square radius, you have to include some irrational number as well. Yes, so because there are some irrational numbers in between, there are some holes in your thing. So I think you're pretty much sure. So then, yeah, one more question. So this is basically the interval 1 minus 1 by n to 2 plus 1 by n. I'm doing intersection of it. We have just discussed this. So if you answer this, then I can be pretty sure that you understood the concept. I'm doing intersection of infinitely many open sets. So what would it be? So this is basically like at n equal to 1, this will be 0 to 3, and then you keep on changing n. So this will maybe change from 0.1 to say 2.9. I'm just giving some random numbers, these are not the actual ones. And then you have say 0.2 to 2.8, something like that, and then this keeps going on till say eventually n tends to infinite. So this will be 1 to 2. So I'm doing intersection of all these sets. So what will happen for the intersection of all these sets? Will it be open or closed? So what would be the intersection of all these sets? Okay, let me ask in a slightly different way. So let's say I have null set. Is this open? Okay, so one of you says no. What about others? Like this is pretty straightforward because in a null set you cannot create any ball of any finite radius because it doesn't have any element, it doesn't enclose any elements, so it's not closed, it's not open. So in R space, the complement of it will be the sequence of all real numbers, and sequence of all real numbers is an open set, which means this is a closed set, right? Now what about this? What is intersection of all these ones, all these sets? Is it open, closed? Which of these options? Open, closed, but not compact, or compact? Which of these is true? So just to put things in context, why are we worried about knowing whether a particular sequence is open or not? What is so important about it? Why do you have to know whether it is open, closed, or something else? And just as we discussed before, the entire thing is we know the strategy, but for that strategy to work, we need to know that a particular solution exists in the first place. And in order to know whether it exists or not, we are going to use a theorem which says that it needs to be a closed and bounded set, and the objective function has to be continuous and so on. So before even solving the problem, we need to know whether our domain is closed and bounded, whether it has any holes, or what kind of domain we are dealing with. We don't know how to solve the problem yet, but we are kind of defining our problem in a proper way. So let's say this is your domain in which your optimization is going to be run. So is this domain open or closed, or what kind of domain it is? I think question is clear, so but no one actually answered. So which part of it is not? I guess there's a typo. Oh, sorry. Yeah, sorry, it's a typo. Okay. Yeah, but what about the original question? So the set A, is this open? What about that? So can I write it as this? This? Like just we discussed that intersection of any open sets will never create new boundaries, so it is not going to create a closed set for sure. But Yeah, as there are no new boundary, like just as we discussed, that just that is not sufficient. That will only tell you that it is not going to be closed. Yeah, of course, here there is no other option. So yeah, since it is not closed, it cannot be compact. So the next option left is open. So yeah, that is fine. But how can you be sure that it's going to be open, or it can also be neither open nor closed kind of things? Since here we are dealing with real numbers, you do not have any holes in between. So this is going to be open. So this is straightforward. But otherwise, you can also have something like the set we have. You can end up in having a set of rational numbers or something, which will not be open set. In this particular problem, you don't have that problem. You don't have that case because you're going to end up only in a set of real numbers. I think one of you have already gave this example in the chart before. So is this sequence convergent? Minus 1 to the power n. Yeah, I think one of you have actually commented it a little time before. Minus 1, 1, minus 1, 1. Yeah. So this keeps oscillating between minus 1 and 1. So you have two different values, so it will not converge. Yeah, it doesn't converge, it keeps oscillating. But if you see, if you construct a subsequence of it just with all the positive values and all the negative values, both the subsequences will converge, but they will actually converge to two different values. Let's say positive and negative values. If and we also have seen the theorem, like if all the subsequences are convergent, yeah, if all the subsequences are convergent and all of them are convergent with the same value, then the original sequence will converge. But here you are having two subsequences, both are converging to different values, then the original sequence will also not converge. Yeah, coming back to here. So this is basically come up with some numbers like this. And once you do intersection of all these values, what are we going to get there? So say n equal to initially n equal to 1, so this will be 0, 3. So as n keeps on increasing, this particular value will keep on decreasing. So from 0, it will keep on gradually increasing up to 1, and the other one will initially be n equal to 1, it will be 3, and then as this keeps on increasing, this will keep on reducing to 2. And intersection of these, so between 0, 3 and 0.1, 29, that intersection will be 0.1 to 2.9. At each subsequent value, you are actually reducing your domain, and it will eventually come to this particular value. This will be the final one. So it will come to 1, 2. And 1, 2 is an open set, right? Did I miss something? Okay. Anyone else has anything in this? If you have anything to discuss, like I'm open for discussion. If you have any point, you can bring it up so we can discuss. I think you don't have any questions on that. So this is again a straightforward question. So if you have 1, 2 infinite, so what do I call it? Can I call it open? Yes, since you have a boundary, it cannot be called open. Can I call it compact or not? Yeah, so shouldn't the set corresponding to n tend infinity be? Yes. as n tends to infinite, 1 to the power minus, oh, you're saying 1 minus or something less than 1. So saying as n tends to infinity, this particular value will tend to, n tends to infinity should have 1 to 10 and something. Yeah, okay, so yeah, I understood your point. So basically you're saying since this as n tends to infinity, this particular value will actually be close to 0, but then since it's 1 minus some positive value, it will be less tending to 1 minus, okay. In a similar logic, this will tend to 2 plus because this is some epsilon. So yeah, you're correct. So this will be 1 minus epsilon. Epsilon is positive. I think this is what you're trying to say. Or maybe epsilon greater than 0, and or maybe I should say, this is what you're saying, right? So if this is the case, then as epsilon tends to 0, I can write this as 1 comma 2. Yeah, I can hear you. Yes, if this is what you're saying, then it will eventually be that close bracket 1 comma 2 will be the final one. Yes, if that is the case, then it will be a closed set. No, but they are part of all the previous sets, right? Yes, they would survive in the set. Sorry, one minus epsilon shouldn't be in the final set, right? One would be in the, like the one just before it would be in the final set. Like 1 and 2 would be there, but 1 minus epsilon and 2 plus epsilon wouldn't be there in the set, right? Yes, it should be closed. And then it is also bounded, so it will become a compact set. Okay, sorry. Question 7, I think is straightforward, so you don't have any queries. Yeah, question 8 is also straightforward. I think someone already asked this before. So you have 1 comma infinity. So which kind of set should I call this? Obviously, this is not bounded. Can I call this uh, an open set, or should I call it closed, closed but not compact? Which one of these is? It's not compact for sure because it is not bounded. But which one of these two should I call this? Closed but not compact. Okay. Option B because I don't feel it's open. Okay. So what is A complement? Yeah, the complex set, the complement set is definitely open because if you take A complement, so it will be 1, which is definitely open. So A is closed. Minus infinity to 1, right? The last couple of questions are based on Weierstrass theorem. So you have a function mapping from some feasible set S to some R. S is defined by this particular one, and f of x is e to the x. So what can I say about the infimum of f of x? Yeah, these again, so the if you go back to the theorem, the main requirements are essentially you need to have a set, your domain S should be closed and bounded, and function should be continuous. If all of them are done, then you can say that f at times it minimum and then the minimum exists. Is reciprocal of complement set type? I didn't get your question. Is the reciprocal of complement set type? So are you saying that I didn't get your question? So what do you mean by reciprocal of component? Complement? I mean, the definition of closed set is defined like if the complement of it is open, then we are calling it as closed set, right? That's how we kind of define the closed set. So, so I think we are done with question 8. So coming to question 9, what can I say about it? Is there are just 3 steps we have to check whether the function is continuous. If all 3 are satisfied, then it will exist and then you will be able to attain. So which of these are satisfied and which are not? E to the x is continuous. We have just solved this case. So 1 to infinity is closed but not compact. Similarly, instead of 1 to infinity, we are just putting 0 to infinity. So it is closed, but it is not bounded. The last one is not satisfied. So from Weierstrass theorem, you can say, what can I say now? Doesn't exist. Compact and bounded means the same. Compact is basically closed and bounded. A bounded set does not imply it needs to be a closed one, right? Like I can always have something like, say you can have a set like, say 1 comma 2 minus 1.5. So this is bounded, but I think that's what you asked. This compact and bounded means the same. Compact and bounded. Compact is basically closed plus bounded. Like you need to have a closed set and it needs to be bounded. Only then you call it compact. I just split it into 2 things. That's it. If you want, I can write it as compact and say it is not compact. Okay. So you're saying basically solution does not exist. I mean, infimum does not exist. But okay, what about function e to the x? So do we know what is the minimum of this function? Like forget about optimization, whatever we have discussed. Like you know what is the minimum of this function, right? If you plot e to the x on this particular domain, what is the minimum value? Yeah, 1. And so you know 1 is exists and it is also kind of true, right? Like it is existing, right? How come the conclusion is wrong here? The conclusion from the theorem says that it does not, you kind of said it does not exist. So where is, like, why did it happen? So is Weierstrass theorem just kind of a necessary condition, or it's kind of not a very strong condition? Is this a weak condition, or what can I say about it? Okay, let me put it in a slightly different way. So Why do we need our function to be continuous? In that particular theorem, why do we need the function to be continuous? I think then that is the account for if the minimum occurs at the boundary or not. That's exactly where you have the boundedness coming into picture. So why do we need it to be, so first thing is why do we need it to be closed and why do we need it to be bounded? That's where your problem comes. So if only if it is bounded, then it should be able to account for both the, if particular minimum occurs at the boundaries, then they will be included in the point only if the function is bounded. Sorry, only if the domain is bounded. That's why we need that particular domain to be bounded. In this particular case, it so happens that the minimum is occurring at 0 and it is also included in the set. So it shows up, but in general, it may not always be the case. It can also happen that your, instead of e power x, if I take e to the power minus x, then it is going to occur at the other end, which is not included in the set. So in this particular scenario, it happened to be that minimum is occurring at a boundary which is already included in the domain. In general, which may not be the case. But the point is always like as you said, so boundedness is required because we need to ensure that the minimum lies on the boundaries and it needs to be captured. So why do we need it to be closed? Okay, let's not even go very close. Why do I need the function to be continuous? Let's go in a sequence. Why do I need the function to be continuous? If you recall that the strategy that you are going to implement is more or less in the same three ways. So basically, you will generate a sequence of your design variables or your whatever x you have here. So in this case, x, you will have different values of x. And if this particular x is converging over time, then f will also converge only if f is continuous. Right? That's how we define continuity. So if a function f is continuous, then it means that it is continuous at every point. So if the different values of x that are generated over time are very close to each other, then the function values will also be close to each other. So if the function is continuous, then we will have this particular sequence, a convergent sequence will giving me a convergent function. And that's why we need the function to be continuous. And if it is closed, then the boundaries are, of course, even before that, we started saying only when you have a bounded sequence, then you will have at least one that will always converge. That's the first theorem. Every bounded sequence will have a convergent subsequence. So by ensuring that my domain is bounded, I'll ensure that I can generate some sequence in it, which will be convergent eventually. So once these two are done, then comes the closeness. That's where the point that he has mentioned, that if in our particular case, a minimum is happening at one of the boundaries, then those boundaries have to be included in the domain. Otherwise, I will not be able to attain them. So that's about how do we attain them. So if it is bounded, then we will be sure that you can attain those things. Yeah, in this particular case, we know that the minimum exists and it is attained. This is for this particular case because at x equal to 0, that particular value is already included in the domain. So we don't have to worry about the other end. But in general, it may not be. So it's not very strong condition in such, it's kind of a weak condition. So if Weierstrass theorem is not satisfied, it doesn't mean that infimum does not exist. But if it is satisfied, then infimum exists. So in that sense, it's kind of a weak condition. Just to make sure that you understood whatever we have discussed now, you can kind of quickly tell me what is for this particular function. Okay, okay, x belongs to R. So again, the same three conditions. So you can quickly answer. So first, what can I say about the domain? The domain is x belongs to R. So that is an open set. So it is not closed. It is not bounded. And what about the function? Yeah, it is discontinuous. So function is not continuous. The domain is not closed. Domain is not bounded. So, but so none of the conditions are satisfied. So can I go with this? We will go with does not exist. But let's say you can see the function. Can you tell me what is the minimum value of this function? Yes. So in the limit of x tends to 4 minus, you will actually have minus 10, and that should be some minimum value. So there is some minimum, that there is some infimum, but then the problem is you will not be able to attain it with the particular values of x that you are choosing here. You do not know what exact value of x that will give you that, like it won't be minus 10 exactly, because at x equal to 4 it will be x square. So it will be something that is 4 minus infinity. No, I would want it to be minimized, a whole point. No, there are two different things. We are not talking about the values that the function can take. The set is basically the domain. My domain is x. X is all the set of real numbers. It's set of all real numbers. There are no holes in the set of real numbers. I mean, at least that's what we kind of believe, like kind of an axiom thing. So there are no holes in it. It's just that the function is discontinuous. Nothing wrong with the domain. Yeah. So your function is discontinuous. So as x tends to some 4 minus, so some 4 minus epsilon for some positive epsilon, your function will keep on minimizing. As you will keep on reducing your epsilon, your function value will keep on reducing. In the limit, it will be minus 10, but then that limit will not exist. So there will be a minimum, but you will not be able to attain it. But anyways, so there is a minimum, but then you will not be able to attain it because the function is discontinuous. So you can have, since it is an open set, it is an unbounded set. So none of the conditions are satisfied. So it is not closed, so it is open, it is not bounded, the function is not continuous, none of these conditions are satisfied. So you cannot directly apply the theorem as such. But in most of the problems that we are solving, say in engineering case, we'll have objective functions that are more or less continuous. Even stronger conditions comes in terms of differentiability in the upcoming lectures. And then our domains are basically on some physical variables which are always bounded because of some physical laws. So we have some closed, bounded, and compact sets. So basically we have compact sets as our domains, and our objective functions are always chosen to be continuous functions. So this theorem will more or less always hold. So we can be sure that there will be a minimum. The only problem is how do we go about achieving that minimum. So the entire first week lecture is about ensuring that there is a solution. Only if the solution exists, how do we go about improving our, coming up with ways that we can achieve that solution. I think you can go through the assignment problems. They're more or less similar to the questions that I've discussed now. Are there any queries? These are the questions I have for this week. So if you have any queries, we can discuss them. Resources. Okay, I'll have to discuss with the professor and I'll let you know. Yeah, I'll have to discuss with the professor and I'll get back to you. Maybe I'll let you know in the discussion forum or in the next week lectures with more math. Okay. Yeah, that's all from my side. If you have any questions, yeah, if you have any questions, we can discuss them. Yeah, otherwise, yeah, those of you who do not have any questions, feel free to leave the session. Yeah, those of you who are still in the sessions, you have any questions or queries? Okay, there are no more questions. You're welcome. If there are no questions, then maybe I'll end the session for this week. We can meet next week the same time, or maybe I'll wait for a couple of more minutes. So if someone joins and they have a query, I'll keep the session forum open for discussion. If you have questions, we can discuss. Otherwise, feel free to leave the session. I think you have happen to join in the last. So do you have any specific things that you want me to discuss? You happen to join just a couple of minutes back. Yeah, yeah, sure. The initial ones. If you are familiar with what sets are and then what continuous and differentiable, like if you know how these things are, that should be fine. Only the first week of lectures are more into sets and stuff, but once we go after that, it will be more into differentiation stuff. So you are an undergrad, or so it's like what is your background? So you're from like BTech or undergraduate? Okay. So then your undergrad math is fine. You might not be requiring more than that. Just that you have joined late. We have discussed a lot of questions before you joined. Maybe all these sessions are recorded, so they will be uploaded on YouTube, and the link will be shared with you, so you can go through those. This file also will be shared with you. You can see the questions and solve them yourself. And have you gone through the lecture videos already? Okay, so do you have any queries in them? Okay, sets, yes. So if you have any, yeah, yeah. So if you have any difficulties, let me know in the sessions so we can discuss it in the live session. I mean, the whole aim of the sessions is to kind of help you solve the assignments. Of course, we won't be discussing the solutions directly, but in general, if you have any problems in the conceptual things, or we can discuss if you don't understand any part of the lecture videos, we can bring it up in the session so we can discuss them. You are the only student left, so if you don't have any queries, then I can call it a day for this. Okay. Thank you. I'll see you next week.